In our study of KSP equilibrium problems, there are four main types of equilibrium KSP problems that we'll encounter. In this video, we're going to focus in on the third type, number 3, will a precipitate form? And the way we go about solving these problems is you're going to calculate Q and then compare Q to K, determine the type of shift, and the direction in which it shifts will tell you, yes, a precipitate forms, or no, a precipitate will not form. So up above, you'll see here, when Q is compared to K, we can determine the shifts. If KSP is greater than Q, the system is not at equilibrium, going to shift forward. And in KSP problems, in the forward direction, you're making products, and products are aqueous ions. So you're going to favor the side of the reaction of aqueous ions, so no precipitate forms if it is a forward shift. If KSP is less than Q, then we know we're going to shift in the reverse direction. And in KSP problems, the reverse shift means you're going to make reactants, and that is going to be a solid ionic compound. So if it is a shift in the reverse, yes, a precipitate will form. So these problems are fairly straightforward. You calculate Q, compare Q to K, determine the shift. If it shifts reverse, yes, precipitate forms. If it shifts forward, no, precipitate does not form. So let's take a look at example problem number 8. We're taking iron 2 nitrate, mixing it together with sodium hydroxide, and it's asking us, will a precipitate form? So I say, what is Q? And then compare Q to the KSP value. So what is the potential solid that can form? They're telling you right here, potentially iron 2 hydroxide can form, because what's happening? You're taking a solution of Fe2+ and nitrate ions, 20 milliliters of it, 0.100 molar, and you're adding it with another solution that contains sodium hydroxide, sodium ions, hydroxide ions, 40 milliliters, 0.0500 molar. And when you mix them together, now you have all 4 of these ions floating together. And the one potential solid precipitate that can form is the iron 2 hydroxide. So when the iron pairs up with that hydroxide, potentially we can make a solid. And this question is asking us, does that happen? And because the other combination, sodium with the nitrate, we know that is always soluble, so that's not the possible precipitate that is going to form. Okay. So here, when I combine these two, when we mix them together, when you mix solutions, that means you're diluting the concentrations of these ions, because now the total volume of the 20 mils plus the 40 mils is 60 milliliters. And so when I go and calculate Q, I have to be mindful that I've changed the molarities of the iron ion and the hydroxide ion. So I have to recalculate those molarities using the dilution formula. Okay, so let's go ahead and do that. What is the concentration of Fe2+ in this new solution? And what is the concentration of hydroxide in that new solution? So you can go about this several ways. Pretty much what you're going to do is calculate the moles of iron that were in the original 20 milliliters, 0.1 molar, and then divide that by the total volume of 60 milliliters. Okay, so you can do that. So in this first solution, the moles of Fe2+ would be your 0.02 liters times 0.1 molar. So that equals 0.002 moles of Fe2+. So the concentration inside of our new solution will be equal to 0.002 moles of iron over the new volume of 0.06 liters. So the concentration of iron in our new solution is going to be 0.033 molar. Okay, and we're going to repeat this process for the hydroxide ion. Originally, the hydroxide ion was in 40 milliliters of 0.05. So the moles of hydroxide equals 0.04 liters times 0.05 molar. So 0.002 moles of hydroxide. So the new molarity of hydroxide is also going to be 0.033 molar. Okay. Now that I have the new concentrations of both the iron and the hydroxide, those are the concentrations that I want to plug in to Q. Okay, so we're going to take these guys that I'm highlighting, we're going to plug that into the Q expression. So what is the Q expression? Well, we have to write out our balance equation for what is potentially being formed. Potentially we're making iron 2 hydroxide solid, and we want to know how that dissociates. So you write out the Q expression or the balance equation for iron 2 hydroxide, and you write the Q expression. And we can even call it QSP just to keep it straight from the other Q's. Since we're in solubility land, we can write that SP for solubility product. Remember, Q is the same exact thing as K, it's just non-equilibrium conditions. So it still has the same formula, products over reactants, okay? Coefficients become exponents. That's your Q expression. Now you're going to take the initial concentrations of iron and the hydroxide, plug them into Q, solve for Q. So our QSP equals 0.033 times 0.033 squared. You get a QSP value of 3.59 times 10 to the negative fifth. And the last step, we need to compare Q to K. So remember, if you write your KSP versus Q, you write them in alphabetical order, K before Q. Write the values underneath of them. The KSP value is 8 times 10 to the negative 16. Okay, so KSP is less than the QSP. And when KSP is less than QSP, that QSP is too big. And in order to establish equilibrium, the value of Q is going to decrease until it reaches the value of K. So therefore, this is going to be a reverse shift. So therefore, it's going to shift in the reverse direction. Okay, so we're going to favor the side of the reactants. And look at what is on the reactant side. Solid iron 2 hydroxide. So because this is a reverse shift, we will end up making a precipitate of iron 2 hydroxide. So the answer is yes. Iron 2 hydroxide precipitate forms. And your justification is your calculation of Q and then your comparison of Q to K. So let's take a look at number 9. I want you to hit pause. You try number 9, then you come back and check your work. Okay, will a precipitate of magnesium fluoride form? So again, I ask myself, well, what is Q? Then I need to compare that Q to the KSP and then determine the shift. And if it shifts towards the reactant side, then yes, a precipitate will form. So we need to calculate Q by plugging in the new molarities of our ions. So what are the two ions that are going to be present in this possible precipitate? Magnesium and the fluoride. So I need to calculate the concentration of magnesium 2+, and I need to calculate the concentration of the fluoride ion. So I'm going to go about this one slightly different. If you follow the format from last example, it works just as well for this problem. But those of us looking for a different way to solve this, we can use the dilution formula, which might be a little bit more straightforward for some people. So the dilution formula, remember, is M1 times V1 equals M2 times V2. The 1s represents your starting concentrations and starting volume, and then M2 is after dilution. And V2 is the total volume after dilution, after things have been mixed together. So for the magnesium, originally its molarity is 1.5 times 10 to the negative 3 molar. And when you use this dilution formula, you can leave the the volumes in milliliters if it had milliliters. In this case, it doesn't, it has liters. M2 is what we're solving for. V2 is the total volume. So we took 0.1 liters of magnesium chloride together with 0.2 liters of sodium fluoride. So the new volume is 0.300 liters. And we'll solve for M2, which is the concentration of Mg2+. Okay. Initially. I'm sorry, maybe not right away, Mg2+. This is the concentration of MgCl2 initially, but look here, you have one magnesium ion, so since a 1-to-1 ratio, yes, it is going to be also the concentration of magnesium 2+ ions. So we get a value of, for magnesium, 5 times 10 to the negative 4 molar. That is the starting initial concentration after we've mixed everything together. Now we're going to repeat this process for the fluoride. And switch colors here. Let's go to green. Okay, repeat for the fluoride, and we'll use M1V1, M2V2 as well. So originally fluoride came from this 0.025 molar sodium fluoride solution, 0.2 liters. M2, total volume is 0.3. So M2 equals the concentration of sodium fluoride, which is also the concentration of the fluoride, 1-to-1 ratio. So the concentration of the fluoride is 0.0167 molar. So now that I have my concentrations for magnesium and fluoride, we plug that into the Q expression. So the product, the solubility product, we're making MgF2 solid. Trying to see if that is going to precipitate. Okay, I have my equation. Now we're going to write the QSP expression. QSP, products over reactants, use coefficients as exponents. So QSP equals, I'm plugging in the molarities that I calculated for the magnesium and the fluoride. And I get a value of Q, 1.4 times 10 to the negative 7. So there's the QSP for this scenario. Now, final step, compare Q to K. So KSP versus QSP. The KSP value is 3.7 times 10 to the negative 8. So KSP is less than QSP. That QSP is too big, so it needs to get smaller, so we need to make more of the reactant. So this is going to be a shift in the reverse direction. And so yes, MgF2 solid precipitate forms. Number 10, will a precipitate of silver chromate form when we take 1 milligram of sodium chromate and add it to a solution of silver nitrate? So again, we want to calculate Q, compare the Q to that KSP, determine the shift. So I want to determine the molarity of the silver ion and the molarity of the chromate ion and plug those into the QSP expression and compare Q to K. So for the silver, we're taking 225 milliliters of 1.5 times 10 to the negative 4 molar. And we're adding solid sodium chromate. So unlike the previous examples in which we were mixing two solutions together and we then had to use a dilution formula to calculate the new molarity of the ions, when we're taking the solid sodium chromate and adding it to this already existing solution of silver nitrate, what they failed to tell you is adding this solid sodium chromate, volume doesn't change. So since the volume does not change, this molarity for the silver nitrate remains the same. So we have 1.5 times 10 to the negative 4 molar silver nitrate. So therefore, the molarity of just the silver ion, because that 1-to-1 ratio, is 1.5 times 10 to the negative 4 molar. Okay, so I have silver. Check. Now for the chromate. Chromate comes from the sodium chromate solid that we're adding. So we need to know how many moles of chromate ions are going into the solution. Then I can divide by the volume and I get the molarity of the chromate ion. So if I take 1 milligram of sodium chromate, I know 1 milligram, I can convert that into grams because there's 1,000 milligrams in 1 gram. Then convert that into moles of sodium chromate, molar mass of 161.98 grams. And I get moles of 6.17 times 10 to the negative 6 moles of sodium chromate. And because of that 1-to-1 ratio, that means we also have 6.17 times 10 to the negative 7 moles of the chromate 2 negative ion. So the concentration of the chromate ion will be equal to its moles over the liters. In the liters, we have 225 milliliters, so that's 0.225 liters. And we'll get the molarity of the chromate. We have 2.74 times 10 to the negative 5 molar. There's our chromate 2 minus concentration. That's the value that I'm going to plug into Q. So for Q, I should start by writing out our equation. The solid is Ag2CrO4. That will dissociate into 2 silvers and 1 chromate. So your QSP expression will be Ag plus squared times chromate. And now let's plug and chug our values into the Q. Silver is 1.5 times 10 to the negative 4, and chromate 2.74 times 10 to the negative 5. And let's real quickly solve for Q. Q equals 6.17 times 10 to the negative 13. Final step, compare Q to K. So write them in alphabetical order if you want to use a little arrow trick. The KSP value is 1.1 times 10 to the negative 12. Okay, so 10 to the negative 12 is bigger than 10 to the negative 13. So QSP is too small. So it needs to become bigger, and the only way to become bigger is to have more products. So this is going to be a shift in the forward direction. And if we shift forward, moving this way towards product, look at what is on the product side, aqueous ions. So the answer is no Ag2CrO4 solid precipitate forms, and that is because K is greater than Q. So no silver chromate solid precipitate form. So no, maybe I should write silver chromate precipitate does not form. All right, to recap, will a precipitate form in all these problems? We calculate Q, plug in the molarities of the ions of the potential solid, and then compare Q to K. If Q is bigger than K, it's going to be a reverse shift. Yes, precipitate forms. If Q is smaller than K, then it's going to be a forward shift and no precipitate will form.